Hello, and welcome to the latest edition of Comparatively Speaking, where we use analogies to teach chemistry, or in other words, we use something I was good at in high school to teach something that I was bad at in high school. Now, my outfit for today is by student request that I keep it consistent throughout Unit 1. So we're still in atomic structure, so I'm gonna wear the same thing. And who are we kidding? I wear this a lot anyway. In fact, I sort of resisted because, you know, if I blow up and then I'm wearing this on the street, it's gonna be so easy to recognize me. So like, I'm not worried about that. Anyway, so welcome back everyone. Today is average atomic mass, which is a difficult concept to teach anyway, and was challenging to come up with an analogy for, but it does build on the previous lesson. If you look at lesson 2, the isotope cans, the notion that an isotope is any atom that has, you know, a more or fewer than expected number of neutrons. We know that it's a particular element because of the number of protons. Those are the crust of the pizza from lesson 1, the pizza analogy. So if I keep those protons consistent, I can have, you know, trillions, I can have the entire universal abundance of those atoms, and they're all going to be the same element, but they may differ a little bit in how many neutrons they have. If I just take one single isotope, like one atom of any element, it has a set number of neutrons. There's none of them that have like, you know, half or anything. It's going to have its number of protons, and then that individual atom has whatever number of neutrons it has. So why is the number on the periodic table a decimal number? Why is it a non-integer number? Because it's what's called a weighted average. So, first analogy. Imagine that I give a quiz and everybody in the class gets 100 except this one kid, it's probably Andrew Asher, who gets a 0 on the quiz, right? What if I say that the class average was a 50? And I say, hey, I had 2 scores. I had 0, I had 100. I averaged them. The class average is a 50. Well, it's immediately apparent why that's not fair. Because the 50, the average, is not an abundant number at all. The most abundant number for the score was 100%. Most people got 100 on the quiz. That was the most common number. So a weighted average factors that into account. Now let's take that same analogy and talk about carbon. We like carbon because we know, I like carbon because I'm a science teacher. I'm not gonna assume that you like carbon. I like carbon because I've got 6 protons and almost always I have 6 neutrons as well. But in very rare occasions, I might have 7 neutrons or I might have 8 neutrons. Still carbon, 6 protons. But my nucleus is going to be 6 and 6, or 6 and 7, or 6 and 8. And as we talked about in isotope cans, the 6 and 8, where you've got those extra neutrons, is a little unstable, potential to decay, to drop those neutrons and release them from the nucleus. So if I'm talking about the mass of carbon, most of the time, you do the math there, atomic mass, protons plus neutrons, it's 12. Occasionally you get an isotope of like a version with a mass of 13, and occasionally you get one with a mass of 14, but most of the time it's 12. So to average them and just say like, oh, the average mass of carbon is 13, it's really not accurate. It doesn't factor in the abundance, the number of carbon atoms in the universe that are just 6 and 6 for a mass of 12. So I do something called a weighted average. Now the equation for this, and I don't know if I'm ever gonna get around to subtitles or editing or any of that stuff. All of this has been like one take, upload it. So maybe I'll put it in the comments or something. You know, the equation for this is the abundance of the atom, like how common it is, out of 100%, out of the total, you know, in the universe, what percent of those have this particular mass. So it's the abundance times that mass plus the abundance of other isotopes times their mass. So carbon, I would say, you know, 99.98% of the atoms in the universe have a mass of 12. So I want to convert it to a decimal. I say 0.9998 times 12. And I'm going to get a number that's, you know, it's pretty close to 12, but it's smaller than that. And then I add to that 0.001 times 13 until I get my total Like for each of them, what you're saying is how many are there that are this weight and how heavy is it? So the abundance times the mass plus the abundance times the mass plus the abundance times the mass. One more analogy for that, which is a wrestling team, or really any sport where you have a weigh-in, where you compete by weight class. If you say the wrestling team that's coming to compete against us this week weighs 800 pounds. Maybe that's good news, right? Maybe you have 8 matches against like little guys that I could take, you know? So maybe 800 pounds is a wrestling team that you can beat. But if that 800-pound wrestling team shows up and it's just 3 guys or 3 wrestlers, then you're in a bit more trouble. So just a flat average doesn't always tell you what you need to know. A weighted average says, in that example, how many wrestlers are at a particular, you know, in the 250 and over category, or 220, sorry, Keontae, and how many wrestlers are in the, you know, 120 category. And then you do your abundance, right? How many out of your total times your specific mass. We're going to come back to this a lot, this notion of how many and how heavy. When we talk about atoms and molecules, very often in the lab, we're looking at like how many are there and how heavy are they. So this concludes the lesson number 3 of our review for atomic structure. And I know that you have your choice of people who will gesticulate with their hands and not get around to putting the equations online, and I'm glad that you've chosen this particular person on this particular evening. Thank you for joining us.